So here's a problem in which I want to take this cyclohexane skeletal structure that's tri-substituted and convert it into the chair representation. And I want to draw both chairs and then determine which of the two chairs is the most conformationally stable. So if we start drawing the chairs, we will draw, let's start a little bit lower. Goodness, gotta draw straight lines. And if we number these, it doesn't matter how you number them because we're not here to name them. We're not naming this molecule. So I'm just going to call that carbon 1, carbon 2, and carbon 3. So you see I'm going in a clockwise direction the same way I did in the skeletal form. Let's make some annotations here so we can keep track of it. Because this methyl group here is wedged, that guy is up. That is down because it's a dashed line, and the propyl is also down. So at carbon 1, we have two bonds that we need to take care of. We have the axial bond and then the equatorial bond. Now, when you look at carbon 1 in that chair, which is the up bond? Do you see how this carbon right there is pointing down? And then that is pointing down with respect to it. So it's this guy right there that is pointing up with respect to carbon 1. And we see at the skeletal structure, the methyl group is up. So we have to put the methyl group right there. And then that would mean the hydrogen that's I'm drawing right now is going to be down. Do you see how that hydrogen is down? And it's down right there. If we go to carbon 2, we see that we have an axial bond up and an equatorial bond down. And we see that our ethyl group in the skeletal structure is a dashed line, so that means it's down. And that the hydrogen that's not shown is up. Carbon 3, we have a bond down and a bond up. And so the propyl group, the PR, okay, is down. And so our hydrogen that's not shown here, we could draw it now, that is up. And you can see that hydrogen is up with respect to carbon 3 right there. So that's one of the conformations of this chair. Now we have to do the ring flip. And when we do ring flips, we have to use the first chair that we used as our reference point. So I'm going to zoom out a little bit here so we can view both of them at the same time. So now, when I drew my first chair, I drew my lines like that. So when we do the chair flip, we just have to draw the lines in the opposite direction. And then connect it via the triangle like that. Now in a ring flip, this carbon goes up, that carbon goes down. So that is going to be carbon 2, that's going to be carbon 3, that's carbon 1 now. Now we can just use our first chair as our guide to help us out. Because we know at carbon 1 here, we're going to have an axial up bond and an equatorial down bond. Okay. And so at carbon 1 of the first chair, what do we see about the methyl group? We see that it is in the equatorial position. So that means that it has to be in the axial position when we do the chair flip. And so one thing that I want to highlight here is that this methyl right there is in fact equatorial, and it is also up with respect to carbon 1. When we go to the second chair, we can see with respect to carbon 1, the methyl group is up and it's axial. So do you see how the up position does not change when you flip a chair? But what does change is equatorial to axial. So if we go to carbon 2 now, we see that in the first structure, oh, that's not carbon 2 now, is it? Carbon 2 right there, the ethyl group is equatorial, so now it has to be axial. And if we do the same thing again, notice that ethyl group right here is down. It's still down. Here it is equatorial, and here it is axial. Carbon 3, we have a bond that goes straight up, that's axial, and then an equatorial bond that goes like that. Carbon 3 here, that is axial, and it's down. And so the propyl group has to now become equatorial because those flip. So now we have the equatorial propyl group, and we can see that it is still down. That equatorial position is pointing down with respect to carbon 3. So now if we clean this all up a little bit so we can make sure we're seeing it clearly. Okay. Now between these two chair conformations, which one is the most likely or the most stable one? Just remember this general rule that you want the largest substituents on that cyclohexane ring to be in the equatorial position. So I see a nice bulky methyl group right here in the equatorial position and a ethyl group in the equatorial position, whereas this guy is axial. If we go to the second chair, we have let's keep the color code the same. We have that equatorial, which is good, but then we have these bulky groups here that are axial. So when we compare the two, we have 3 large groups, and if I label this structure A, that structure B, you can see in the structure A, you have 2 of the 3 largest substituents equatorial. Whereas in molecule B, you have 2 of the 3 largest groups that are axial, which is not good. So let me say that again to do the proper comparison, because I didn't say that exactly how I wanted to. So in molecule A, we see we have 2 equatorials, and then in molecule B, we only have 1 in the equatorial position. So that makes this guy right here the most stable chair conformation between those two.